That's correct. Yeah, it's a week from today, which I'll say again at the beginning of class. But yes. That depends on you. I don't believe in that kind of advice. I mean, how do you study for a test in general? How do you study for a test in general? Yeah, so just do that. Should be fine. Yes. Well, remember I said this at the beginning of the term. The quizzes are designed to be the hardest part of the course, right? If you understand the concepts on the quiz, then the exam should be easy, right? Of course, you should also do practice problems because the quizzes don't always emphasize computation as much, right? Whereas like the practice homework problems do. So yeah, I mean, like, I would say just thoroughly review the solutions to the quiz and, you know, just do the homework. And if you have any questions, I was thinking of probably I'll hold some extra office hours next week or something, so we can address any questions you might have. Everything that we covered through today. Yeah. Sure. Yeah. I mean, you know. Sure. I mean, you know, it's just what's on the syllabus up to what we covered today, but sure, I can, yeah, it's fine either way, you know. Hey, yeah. An HDMI adapter. I don't think we have anything that unplugs from this. Yeah, I'm not seeing it. Sorry. Wait, oh, here's a bag of stuff. No, this is just a microphone. Sorry. Okay, so we've been having a little bit of discussion here about the exam that's going to happen a week from today in class. So exam one in class next Thursday. Three, right? The third, yeah, pretty sure that's right. So the other thing that I found out yesterday or Tuesday, I forget, the course coordinator decided that all the exams will be allowed a note sheet that you design, right? One page, just front, not front and back. Okay, so note sheet allowed. What's the standard size? 8.5 by 11, one side. Okay, this is I'll send a Canvas announcement with all this information as well, but you know, I guess it's good to say it. Right. Exam will cover everything we've done. Through today. Okay. Furthermore, I'll send out practice exams. Tonight. Solutions on Monday. Right, so maybe, hopefully, this will be enough time for you to actually try them in a vacuum, and then I'll give you the answers on Monday. Yeah. Okay. So also, just remember that in general, the quizzes are the hardest thing, right? This is the way the course, I decided to design the course, right? So if you have complete mastery of the concepts on the quiz, you should have a fairly easy time on the exam. All right. Okay. Oh, one other thing. If you happen to be attending remotely, you know, things change day by day, of course. As long as you're able, like physically able, you're expected to take the test at the same time, even if you are remote. Okay. If that's a problem, if you're too sick to actually take the exam, just email me and we'll arrange a time to do a makeup exam. Okay. Okay. Good. Any other questions about the exam? All right. Good. So let's remind ourselves. I told you a theorem at the end of yesterday, and I just want to do a quick sketch of a proof, some justification of this theorem. Right. So let's remind ourselves of what the theorem says. We'll take f, a function with domain E, real valued. If f contains a local extreme value, at some point P in the domain, then P is a critical point. Of f. Right, and remember, we recapped yesterday, a critical point is a place where the gradient of the function is the zero vector, or we're not differentiable at the point P, right? Two kinds of critical points. And in the second kind, the kind where you're not differentiable, that includes the boundary of E, right? This is akin to calculus 1, right? If you have a closed interval as your domain, you're not differentiable at the endpoints because you can't approach from both sides. Same thing with the boundary of E, right? This is the scenario that we drew yesterday, right? Here's our M. Here's E. Right, and our function f goes to the real line R. All these points, this entire boundary, these are all critical points, right, which are included in E. I drew it using our convention, right, where an open set is indicated by a dashed line and a closed set, the boundary is contained, we have a solid line. All these points on the edge are critical points because we're not differentiable at them. We can't approach from any direction. Yeah. Okay. So, here's some justification of this fact. So let's assume that P is a local extreme value. Then we have U, a subset of Rn, open, containing P, so that f of P is a global extreme in, remember this set, the intersection of E with U. Okay. So that's just the definition of what a local extreme value is, right? So here's what we're going to do. Consider a new function. Which I'll define as g of x sub I equal to f evaluated at P1, comma, P2, up through P sub I minus 1, x sub I, P sub I plus 1, all the way up to Pn. Okay, where P hat has these components, P1, P2, up through Pn. Okay, so what I'm doing here is I'm taking the function f and I'm almost evaluating it at P. I'm putting all the components of P in except for the ith one. I'm leaving that as a variable. Okay, so I've created a function of a single variable out of my function of n variables. F. Okay. Okay with that? Good. All right. Then we know this new function g is an extreme value at P sub I, since f is 1 at P hat, right? If I plug P sub I in for x sub I, I'm just evaluating f at P hat, right? So we know the function g attains an extreme value at this point, P sub I. Okay. So now I'm just going to quote you the fact from calculus 1 that we're trying to generalize, right? We know that for a function of a single variable, that if we have a extreme value, then we must be a critical. Right? We know that for functions of a single variable. We're trying to prove that now for functions of n variables. Okay, so this means g prime evaluated at p sub I. So yeah, I'm going to make this claim here. The partial derivative of f with respect to x sub I evaluated at p sub I is equal to 0. Or not differential. P sub I. Right? Again, just the definition of critical point for functions of a single variable. Right? This is well established from calculus 1. Here's the key step, right? How do I have this equality? Why is it that the derivative of g is the same as the partial derivative of f with respect to the variable x sub I? Who can explain that to me? Yeah.
When you do
Yeah, exactly. That's exactly right. What do we do when we take a partial derivative? We hold the other variables constant. Here, we've made that explicit choice. These are actually constants. We don't just treat the variables like constants. We plug something in to g, right? So therefore, when we differentiate g, the only variable is x sub I. That's the same as differentiating f with respect to just that variable. We're holding x1 through x I minus 1 and x I plus 1 through xn all constant when we do this, right? It's what we had in the definition of g. So that's why these two things are the same. Okay. So now this argument holds for all I between 1 and n. Therefore, either the gradient of f evaluated at p is equal to the 0 vector, or f is not differentiable. At right? It could be the case that basically what I'm saying here is we can create n different functions of a single variable, right? It's as I ranges from 1 to n here in this definition. And this argument that either will have the derivative be 0 at p sub I or be non-differentiable means that one of these two things must be true, right? If it so happens that all the g of x sub i's have derivative 0, then we get the gradient of 0. But if even one of them is not differentiable at p sub I, then f altogether is not differentiable at p hat, right? Because one of the partial derivatives fails to exist. So we're not differentiable, right? We can't define the gradient. Okay. So the reason I wanted to show you this proof is because it's essentially just using what you know from calculus 1, right? And just making this clever definition of a function of a single variable. Kind of a direct generalization. That's why I wanted to say this. Okay, so here I want to make formal something that we've discussed in a particular example. If the gradient of f evaluated at p hat equal to the zero vector, the tangent set to the graph of f at p hat has form z equals, just from the definition, f evaluated at p hat plus the gradient of f evaluated at p hat dot x hat minus p hat. But we just assumed that the gradient was zero. So what do we get? Just v is equal to some constant, right? Okay. This is the meaning of having a horizontal tangent set. Okay. Remember we talked about this when we were talking about level sets and gradients, right? I asked you to find where a certain level set had a horizontal tangent plane. And it's like, well, what do we mean by horizontal? Well, we just kind of waved our hands and said parallel to the XY plane or perpendicular to the Z axis, right? So that's actually in general what we mean when the tangent set is just an extra variable equal to a constant, right? So this generalizes a horizontal line, a horizontal tangent line on a curve, or a horizontal tangent plane to a surface. Just means that we have a tangent set of this form. The gradient term drops out because we have zero gradient. Okay. Okay. Great. So here's a definition. A saddle point p hat of f is a critical point. Sorry, that we already defined what a critical point is. Critical point at which f is differentiable which of course I mean that the gradient of f evaluated at p is equal to the zero vector. But f evaluated at p is not a local extreme value. Right. So this is these are the counterexamples to the converse of our statement of the theorem, right? That is to say, if we have a local extreme value, we know it's a critical point. Not all critical points are local extreme values, right? Because we have these things, saddle points. Okay, so let's look at an example, and then in a short while, I'll attempt to make some drawings that illustrate what these things are like. And you might have a guess the use of this word saddle. We've seen that before, right? let's take the function f of x comma y is equal to e to the negative x squared times 3 minus y to the 4th over 4 plus 5y cubed over 3 minus 3y squared. Find all critical points. Okay, why don't we take a couple minutes and just do this for practice, right? This is a completely mechanical thing to do, right? Okay, maybe we should discuss how to approach this problem. What should we do in order to find the critical points? Yeah,
So
great. So we'll find the gradient and then do what? Exactly. That's one type of critical point. How about the places where f is non-differentiable? Yeah, this is in fact differentiable everywhere, right? So we don't have any critical points of the second kind where we're not differentiable. Yeah, so right, we didn't say what the domain is, but it doesn't matter because it's differentiable everywhere. So no matter the domain, unless it's closed. We're differentiable everywhere. So again, thank you for saying that. Whenever I don't say what the domain is, just if it's an elementary function, if it's defined everywhere, you assume the domain is everything. Okay. So we'll go ahead with this procedure looking for critical points of the first kind where the gradient is 0. Okay, so what's the gradient? Partial derivative with respect to x is what? Yeah. Times, yeah, the remaining y polynomial, which is just like a constant. Good. I'll write the y component on the next line. How about the derivative with respect to y here?
E negative x squared all times negative y cubed plus 5y squared minus 6y.
Y squared minus 6y. Good, looks good to me. Okay. And we want to find x comma y, where the gradient of f is equal to 0 comma 0. So what do we think about this? Yeah. Yeah, so you want to set each of them to 0 separately because you'll make it easier for yourself that way. Maybe by going through this procedure, we'll see why. You actually end up doing less algebraic manipulation if you don't set them equal to each other. Okay, so yeah. Yeah, good. So in order to make this the x component 0, so here, let me write some of this down. Yes, set these equal to 0. Okay, so then as you were saying, one way we can get this to be 0 happens when x itself equals 0, right? Because we have this factor of x out front. Okay. Good. Now, the partial derivative with respect to y equals to 0. When does that happen? Yeah. Yeah, and when else? Yeah. Okay, so that was a trick question. E to the negative x squared is never 0, right? It's an exponential. It's always a positive number. So yeah, in other words, we need a root of this polynomial, a y value that sets this polynomial equal to 0. Okay, so happens when negative y cubed plus 5y squared minus 6y is equal to 0. Now we refer back to high school algebra, right? We need to solve this polynomial. How do we solve a polynomial? What's one tried and true method that we can use often? Yeah. Yeah, we should try to factor. And we know we can factor a y out right away. In fact, maybe it's nicer if I factor a negative y, right? So take a negative y, I get y squared minus 5y plus 6 equal to 0. I can factor this further, right? negative y times y minus 2 times y minus 3 equals 0, right? So this happens when y is equal to 0, 2, or 3. Okay. So altogether, the critical points are 0, 0, 0, 2, and 0, 3. Did I miss anything? Yeah. Excellent question. This is exactly what I was trying to ask. Did I miss anything? Okay. Because if I find the roots of this polynomial, this makes fx equal to 0, right? However, the roots of this polynomial are not the same as the roots of this polynomial. So if we choose that value for y, this component will not be 0. Right? Yeah, good question. So yes, in fact, this list is complete. These are all the critical points. Okay. Now, the all-important question. Great, we know how to find critical points. This is just a fairly mechanical algebraic procedure, right? Now, the question becomes, how can we classify them? How do we know which are local maxes, local mins, or saddles? Now, how do we know which critical points are local maxes, mins, or saddles? Well, whenever we encounter a question we don't know the answer to in multivariable calculus, we should look back to single variable calculus and see if we can think of a generalization of what we know from the case of one variable. So, yeah. Okay, yeah, good. So remember the second derivative test for critical points in calculus 1, right? If you're concave up, you're at a minimum. If you're concave down, you're at a maximum. If the concave is 0, you're neither, right? So let's just recall this. Recall in calculus 1, we use the second derivative test. Graph of some function f of x. Here's some critical point C. So the first derivative of f evaluated at C, 0. And the second derivative of f evaluated at C is positive. This implies a local min. In a similar fashion, I guess I should draw this line higher. graph of some function x, and here we have a critical point C. So again, the first derivative of f evaluated at C is equal to 0. And in this scenario, the second derivative of f evaluated at C is less than 0, i.e. conjugate down. Max. And then, of course, we have this kind of cubic situation, right? So again, we have the graph of some function x, some critical point C. And here we have the first derivative of f evaluated at C is equal to 0. The second derivative of f evaluated at C is also equal to 0. It implies 9. Okay, so great. This is the motivation of what we want to do. Of course, however, remember there are how many second partial derivatives? So yeah, remember Clairaut's theorem. When we look at nice enough functions, there's only 3, right? Because the mixed partials are equal. In general, there's 4, but for all the functions we're considering, yeah, there's 3 different second derivatives, right? So we have to do something to collect all that information into one object if we want to imitate what the second derivative test does. Okay, so how are we going to do that? What exactly is the methodology? Well, I'll give you a definition, and then I'll give you some way to use this thing and give you a loose justification of why this works. Okay, so here we go. So let's suppose f of x comma y has continuous second partials. In an open interval. Some point P in the domain. Then the Hessian matrix of F at P is the following. H sub F, you'll see sometimes F X evaluated at P, F X Y evaluated at P, F X Y evaluated at P, Y evaluated at P. Or sometimes for shorthand, you'll just see this. Again, this notation of evaluation, right? Just a vertical bar with a P at the bottom. Just need to plug in P everywhere you can. Okay. Right. So remember when we want to collect all the first order differential information, we collect it in a vector, the gradient. Now, for the second order differential information, we're using a matrix. This is kind of interesting if you know any linear algebra. Yes. So the assumption that f of xy has continuous partials means that those are equal, right? That's a Clairaut's theorem, right? So that's why we make this assumption. You're right. In general, this should be fyx, but using this assumption makes computation with this a little bit nicer. Yeah, good, big graph.
So
We say P is a non-degenerate critical point. If and only if the gradient of f evaluated at P is equal to the zero vector and the determinant of the Hessian matrix which we will sometimes denote just D for shorthand, which if we actually compute what's the determinant of a 2x2 matrix? Remember we went over this when we defined the cross product? Yeah.
x minus or f times fyy minus.
Yeah, exactly. We multiply the first diagonal and then subtract multiplying across the second diagonal, right? So we get this function, fxx times fyy minus fxy squared evaluated at P. And we call it non-degenerate if this is not equal to 0. Okay. So this is all the machinery necessary to generalize the second derivative test from from calculus 1. All right. So again, fxy has continuous second partials. In an open neighborhood. P. And P is a non-degenerate. Then we have the following. Firstly, if D, the determinant of the Hessian matrix, is strictly greater than 0, and fxx evaluated at P is also strictly greater than 0, then f attains a local minimum at P. 2. If the determinant of the Hessian matrix is positive and fxx evaluated at P is negative, then F attains a local mass. Okay. And thirdly, if the determinant of the Hessian is negative, then F has a saddle point. At P. Okay, so what happens if the determinant of the Hessian is 0? Say again? It's degenerate, and we have no information. We can't apply the second derivative test. So this is quite a bit more subtle than the second derivative test of calculus 1, but that's because there's more going on in more dimensions, right? To test a little more. So before we talk about what this means, let's just draw the typical situations, right? So typically, like graphs. Y. Here, let me draw Z is equal to x squared. It's y squared. Get this paraboloid. And it's my Z. I want to draw the graph of Z minus x squared minus y squared. We get this paraboloid that opens down. Okay. X. And of course, our favorite graph, which I draw obsessively, saddle. Graph I've seen many times before. X squared minus y squared. Saddle. So let's think about what this means, these sign tests that we do on the determinant of the Hessian matrix. Think about the simple case. where fxx evaluated at p hat is equal to 0. Oh, sorry, not fxx, fxy. Let's just assume that the mixed partial is 0. Okay, this applies in any case, but it's harder to think about when this is not 0. When this is 0, we can come up with some justification of why we do the sign analysis the way we do in the second derivative test. Okay. Then the Hessian determinant becomes the following. D is equal to f xx evaluated at p hat times f y evaluated at p hat. Okay, right? We lose our subtracted term, fxy squared, because we're assuming it equals 0 in this case. So then if D is strictly positive, what can we say about the signs of fxx and fyy? Yeah. They're both positive or they're both negative. They have the same sign, right? Yeah. Then fxx and fyy have the same sign. Okay, so remember when we first started talking about partial derivatives, we said that first partials behave just the same as derivatives from calculus 1. They tell us the slope of the line tangent to our surface in the single dimension that you're differentiating in, right? The first partial derivative with respect to x tells us the slope of the line that goes through the cross section holding y constant, right? Same with the second derivatives. It tells us the concavity of that cross section, of that curve that is the cross section when we hold y constant, fxx, right? So what this is saying is that if we take an x cross section and a y cross section, both those cross sections will be concave down or concave up, right? So we know we're in either this situation or this situation. If I take a cross section with respect to x here, I get a parabola down. With respect to y, I get a parabola down. The concavity has the same sign, or the second derivative has the same sign. The concavity is the same for both cross sections. Same story here, right? With respect to x, if I take a cross section, I get concave up. With respect to y, I also get concave up. Okay, so having the Hessian determinant be positive means I must be in one or the other of these, right? So to determine if max or min, I just have to determine the sign of one of fxx or fyy. So, I mean, as I wrote it here, I used fxx, but I could also just use fyy, right? And in fact, you might find it easier to evaluate one or the other at the point P. Doesn't matter which one you do, but that's just a lot to write, right? So it's your choice if you want to use fxx or fyy. Okay. So to determine if max or min, check the sign of either fxx evaluated at P or fyy evaluated. And that will tell you if here concave down or concave up. Right? So again, sticking with this simple case, if the Hessian determinant is negative, what does that tell us about the signs of fxx and fyy? They're the opposite signs. Yeah, good. So that's why the test ends there, right? For the Hessian determinant being negative. Because here, if we take a cross section with respect to x, we're concave up in the way of drops, right? With respect to y, we're concave down. So we get a saddle. That's that saddle behavior. So if you travel in one direction, you're at a minimum. If you travel in another direction, you're at a maximum. So it's neither in 3 dimensions. Okay. X and fyy are opposite. Meaning opposite concavity in the x and y cross sections. Okay, so the full proof of this is significantly more complicated when you account for f of x, y being non-zero, but the spirit is the same as this, right? You just have to account for how x and y can be changing together, right? It doesn't exactly record the concavity the same. It's a different notion. We're not going to get into that, but it's in the textbook if you want to read about it. Okay. Okay, good. So let's just do a simpler example than the one we were looking at before. Something that we can compute a little faster. So let's take fxy equal to 3x minus x cubed minus 2y squared plus y to the 4th. Let me ask you to find all critical points. Show they're non-degenerate. And classify them. Okay. So what should we do to start? Yeah. Yeah, we should find the gradient and look for the critical points, right? Again, I didn't specify the domain here, and this is just a polynomial. So we can assume that the domain is all of R2, right? So let's compute the gradient. Okay, the gradient of f, partial derivative with respect to x, what do we get? Yeah. Yeah, 3 minus 3x squared. Good, and the partial derivative with respect to y. What? Yeah. Good. And we'll set this equal to 0 vector. Or in other words, simultaneously solve 3 times 1 minus x squared is equal to 0. And 4y times -1 plus y squared is equal to 0. Okay, so let me give you a preview here. The examples that we've examined so far for finding critical points have been fairly nice to solve simultaneously these equations when we set the gradient equal to 0. This one's especially nice because this only involves x's and this only involves y's. There's no general procedure for simultaneously solving arbitrary algebraic equations, right? We know what to do for systems of linear equations, but for systems of arbitrary equations, you just have to be clever, use whatever you know about algebra. But for now, this is just solving polynomials, right? So what are the potential values that make that satisfy this equation? Yeah, 1 and -1. So x is equal to plus or minus 1. And how about the solution here? What do we get? Yeah, good. And y can be equal to 0 or plus or minus 1. So altogether, how many critical points do we have? Yeah, good. 6. So 6 critical points. All combinations. So 1, 0, 1, 1, 1, -1, -1, 0, -1, 1, -1, -1. Now, yeah, okay. Well, we're kind of out of time here, but now that we've identified the critical points, maybe try to do this over the weekend. We'll pick it up on Monday. We'll verify they're non-degenerate and classify them as maxes, mins, or saddles. So have a good weekend and look out for the practice exams that I'll send out this evening. Okay? Sorry. No, only the final design will be common across all of them. You know, it's variation as how fast people are going. Oh, yes. Can you come to my house? Are you busy right now? Yeah. Okay, yeah. I have. I just. Yeah.
So I booked a room reserve for the DRC to take my midterm
Okay.
there.
Great.
So they should email you asking for the document.
Okay. Fantastic.
Thank you.
Mhm.
Good weekend.
Yep. You too.
You know, I can get like this physical copy of it.
Yeah. Can you come to my office right now? I can give it to you right now. If you can't, can you come later today sometime? Okay. What time? It's good for you.
I think I can.
Okay. Great.
Thank you.
Yep. You too. Yeah. Sure. See you. See you Monday. Have a good weekend.